Okay, honors chemistry people, I have a demo that I want to show you as a video because you'll see why I don't want to actually do this demo in a few minutes. We're going to just walk through this YouTube video really quickly, and I'm going to stop and pause every once in a while to kind of explain what's going on. This is a relatively older video. It was posted about 12 or 13 years ago, so the camera work is not awesome, but it does provide a really good tool. So what we're going to do today in this video is they are going to take the alkali metals. They're going to take lithium, sodium, potassium, rubidium, and cesium, and we're going to compare and contrast their physical properties as well as the chemical properties of them while they react with water. Now, one of the things that we've been going over with the periodic table is realizing that the physical and chemical properties of the various groups or the columns on the periodic table are very, very similar. And they're very similar because they have the same valence electron structure, which allows them to react with things very much the same way. So let's do this video really quick. So let's get this maximized. Here we go.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife.
Okay, I just want to pause right here. Look at how they are cutting this. This is a bar of lithium, by the way. Lithium, they used a scalpel or an X-Acto knife to cut this lithium. Now, if you've ever used an X-Acto knife or a scalpel, you know that those knives do not take a lot of pressure. If you put a lot of pressure on those knives snap. So just think about what kind of properties this metal has to have in order for us to be able to cut it with a scalpel or an X-Acto knife. This metal has to be incredibly soft. And that's not how we normally think of, that's not how we normally think of metals. But the alkali metals are incredibly soft.
In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears.
Okay, another thing here, did you see how quickly that lithium, once they cut it, got black again? That's the idea of tarnishing. It's reacting with the air. We're used to seeing silver things tarnish, but if you have any silver or silver things around your house, you'll realize that the silver around your house tarnishes very, very slowly. And this lithium tarnishes right before our eyes, which means it's extremely reactive with the air. So once again, another chemical property there. The first one is physical. The softness was physical.
Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly.
Okay, so we noticed that the corrosion on the sodium occurred even more quickly than it did with the lithium. So as we go from lithium to sodium to potassium, what do you think the trend's going to be? Let's look at potassium and see if you were right.
With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium.
Okay, I want you to notice that the lithium is floating on the water. We normally don't think of metals as being not dense, but these metals are not dense at all. In fact, they're so not dense that these metals will actually float on water. So it's kind of different. And notice we've got some steam coming off of there, This gas coming off is hydrogen gas. So think about this. Our trends with reacting with air got more and more quick and more reactive as we went down that periodic table, right? Lithium, sodium, potassium, rubidium. Do you think we're going to find the same trends here? Do you think we're going to get more and more reactive? And if we have heat going off of this lithium, do you think eventually we'll get enough heat that this hydrogen gas that is generated? I hope you all know that hydrogen gas is flammable. Do you think we're going to get enough heat that this actually starts to create a fire? We'll see.
The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an...
Okay, I want to show you this right here. This aqueous, this OH that I'm using my mouse to circle, this is why they have the name of alkali metals. So in British vernacular, alkali means what we think of as American English as base. This OH being released into the water solution creates a base or an alkali solution. And because when we put these metals in water, that it creates an alkali solution, that's why they are called alkali metals.
Aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
See